for letting me know. All right, so your test on Wednesday at 3. So first of all, it's going to be multiple choice, and it will be 100 questions. Each question is going to be 1 point, worth 1 point. And that's a lot of questions. It's very different from when you take it online. In general, the questions are slightly easier in the sense that I don't give you any questions to order or the ones that have multiple answers. They're a lot more straightforward in that sense. Also, when I do questions that are open book, I ask things that you can't just look up, right? But in this case, I will be asking some definitions like, what's a black hole, or what's dark matter, or what's dark energy, just things like that, main big concepts. So if you review those, they're pretty straightforward, those questions. So of those 100 questions, let me see if I can, I have to admit, I have to be completely transparent. I'm not super good at using my iPad for Zoom. So, but let me try it. All right, because I know that it's a little better to do this on writing it down, right? So, okay, so here we go. So final review. All right, so first of all, you want to study your homework. That's the most important thing. So study homework. And in particular, I want you to study homework 7 through 10, because out of those, I've already written more than 60 questions. So I don't know exactly how many because I haven't finished writing the exam. Right now, I've written 93 questions. I have 7 more to go. So it'll be 60 something. And then for homework 1 through 6, which was the first couple of midterms, I will be including 30 something questions. So, if you study your homework 7 through 10, you're going to be doing pretty well. You'll have more than 60 questions. I haven't finished writing the exam because I'm trying really, really hard to write 1 question for the final for every 1 question that you have for the homework. I'm being very fastidious about it. So please make sure you study your homework. It's your best way to be able to get things, to be able to do well on your final. I've already written all of that, so you can be sure that there is 1 question for every single question that you have on your homework. For these ones, I'm not going to go one by one. Obviously, that's a lot of questions, and I only asked 30. For that, what I'm trying to do is mostly main topics, main themes. And I will spend a little bit of time today talking about what are the main themes, but you can just imagine what are the things that we talked about over and over again. Fusion in the centers of stars. Like recently it came up when we were talking about the Big Bang, and I was telling you that the entire universe was just like the central part of a star where fusion could happen. So you can be sure that I'm going to be asking something about fusion, that I'm going to be asking something about centers of stars. Things like gravity, right? I talked about gravity over and over and over again. So gravity is going to be there. Gas pressure, we talked about gas pressure and gas pressure versus gravity. So we ask these things over and over again, so they will be there. Then there are things like the life of our sun. Things like, I want you to know where in the universe you live. So I would want you to know the name of our planet, which of course it's a little too easy, so I'm not going to ask that. The name of our star, the sun. So how big is the sun compared to the earth, right? Things like, is the sun going to go supernova? I want you to know what type of star the sun is. And then we are in a galaxy, the Milky Way. So I want you to know what type of galaxy the Milky Way is. And I want you to know, where the Milky Way lives. Does it live in a big, rich cluster of galaxies, or does it live in, a poor group, or and so on. So I want you to know our place in the universe. So those things. So what I'm going to do today is first I'm going to go over homework number 10. That'll be the first thing. Then I'll go over some main themes, and then I'll open it up for questions from you. So I see that I have quite a few questions already. Let me see if there's, and by the way, I opened the chat to everyone so that everyone can see what others are asking. Okay, so you guys are talking about the midterms. Okay, so the question about memorizing, in case you haven't noticed, I absolutely hate memorizing. So I don't like memorizing, because the problem with memorizing is that you memorize things and then you forget them very quickly, right? And I don't mean you in particular, I mean me, I mean most people. So I try to emphasize things that I think there might be a chance that you remember 10 years from now. So there are a few things, right? That, like, I ask you to memorize how big the Milky Way is. That is one thing that I ask you to memorize. I will be asking it. I ask you to memorize how many years after the Big Bang recombination happened. And I'll talk a little more about recombination. But it's something I ask you to memorize. I will ask it, right? Things like I ask you to memorize how big is the sun compared to the Earth. So things that I specifically told you to memorize, yes, you should memorize. The problem with memorizing the homework, just memorizing it, right, is that the questions on the final are different. They're related to each of the questions from the homework, but they're not exactly the same. So if you memorize the answers to the homework without understanding them, you will probably not do very well on the final. So I want you to go through them and learn them and understand them. Things that are definitions, for example, like what is dark matter, yeah, you can memorize that. But again, you need to understand it, because then I might not ask you a definition of dark matter. I might ask you, is the dust in our galaxy dark matter? And if you didn't understand the definition of dark matter, then you're not going to know whether dust is dark matter or not. And by the way, what's the answer to that? Is the dust in our galaxy dark matter? No, that's right. Okay, very good. So let me go over homework number 10. So let me share that. All right, so homework number 10. First of all, what does Hubble's law say? And let me go to, I have the specific slide where I talked about Hubble's law. So Hubble's law, I mean, again, this is one of those where you can memorize it. So Hubble's law says that on average, the recession velocity of a galaxy is directly proportional to its distance. So it's one of those you could memorize, but the problem is, what if I don't use those exact words, right, in the test? So you need to understand what it means. And what it means is that if we observe a galaxy at a certain distance, the recession velocity, or the velocity with which it seems to be going away from us, is not random, it's actually related. And by looking at the distance of a galaxy, you can immediately know more or less how fast it's going to be going away from us, or vice versa. You can measure how fast it's going away from us, and you will know roughly what the distance to the galaxy is. So this is the plot that is associated with the Hubble law. And it just tells us that more distant galaxies, or the more distant the galaxy, the faster it appears to be going away from us. And question number 2 is just an application of question number 1, right? So galaxy M82, I mostly wrote this question because I wanted an excuse to put in a couple of pretty galaxies. So M82 is what is called a dwarf galaxy. Very pretty, very close to us. That's why it looks big, even though it is a dwarf galaxy. But that's pretty close. It's 11.4 million light years away from us. And then M109 is 55 million light years away from us. So this one, M109, is farther away than M82. So by the Hubble law, which if you look at this, galaxies that are more distant are also receding faster. So, and also the recession is measured by redshift. The larger the redshift, the faster the recession velocity. So by the Hubble law, galaxy M109 is going to have a larger redshift than M82. All right, let me set my do not disturb. Okay. All right, so that's question number 2. Those are pretty straightforward. Question number 3, if we are not at the center of the universe, then why does it look like all distant galaxies are moving away from us? And so that question, it just has to do with the fact that the universe is the one that is expanding. Let me see. So if you have galaxies that are in the center of a grid that represents the universe, and if that grid expands, so I can make it expand like this, and it becomes bigger and bigger and bigger, it looks like all galaxies are going away from each other. But it is because the space in between galaxies is expanding. And it doesn't matter where you are, if you sit here or if you sit on this other one, it will look like every other galaxy is moving away from you. So it doesn't mean at all that we're at the center of the universe, the fact that we see everything going away. And since I did a poll in class and everyone seemed to get that right, I'm going to be assuming that, that I don't need to go too much over that unless you tell me otherwise. All right. All right, so what does the cosmological principle say? Why does that imply that the universe has no edges? So let me actually switch to the pad. Oh, this is, no, this is, okay, screen mirroring. Oh, this is going to be a hassle if I had to do that every time. Okay, so let's go to another page. All right, so first cosmological principle. So the cosmological principle says that the universe looks about the same no matter where you are within it. So if we had a universe that had edges, right? And we had a distribution of galaxies. All of those dots are a distribution of galaxies, and they're pretty uniform. By the cosmological principle, let me switch colors here. So by the cosmological principle, if I am here and I look in this direction, it should look about the same as if I look in this other direction. Everywhere that I look, it should look about the same. But the problem with my drawing here is that if I sit here at the edge of this fake universe, if I look in this direction, I will see a lot of galaxies. But if I see in this other direction, I will see no galaxies. Why? Because I'm sitting at the edge of this fake universe. And that would violate the cosmological principle, which says that the universe looks about the same no matter where you are within it. This can only be true if there are no edges, right? So I have to erase the edges. That took a long time. So I need to have galaxies that keep going in every direction, so that when I sit in this point here and I look that way, it'll look like there's a distribution of galaxies, right? The other thing is, if there's no edges, then there's no center. How do I find the center of this square? Well, I measure how many inches there are from one extreme to the other, and then here, and then I take half of that, and that's where I find the center. If there are no edges, then I can't find the center. There's no center because there are no edges. So that's roughly the answer to, what is it? Question number 4. All right, please stop me if it doesn't make sense. What happened about one Hubble time ago? And approximately how long ago that was? In order to answer that question, you need to remember what is one Hubble time? What is it that we call one Hubble time? So let me, right. So the amount of time that we call the Hubble time is the time that we infer that the universe has been expanding, right? So how do we infer that? Well, by looking at every galaxy, we figure out how far away the galaxy is from us. We figure out how fast it appears to be going, and then we just divide one by the other, right? So in this case, for example, a galaxy is 1.4 billion light years away from you. You divide it by the velocity, in this case, 0.1 light years per year. So 1.4 divided by 0.1 gives you 14 billion years. And what I told you is, like, just like in the example of the party, right, where everyone is going at different speeds, and by figuring out where they are, you know, how far away the distance, and you figure out how fast they're going, you can reverse engineer, right? You can do the math to figure out that all of them left your house 1 hour ago. And it's the same with the universe. Everything left your house an hour, no, not an hour ago, 14 billion years ago, right? That's 13.7 to be precise. So that we call the Hubble time, because it comes from the Hubble law. And so so one Hubble time ago, roughly, the universe started, right? One Hubble time ago, we had the Big Bang. And so I think that was the question. What happened about one Hubble time ago? The universe started expanding. And approximately how long ago was that? About 13.7 billion years. All right, next question. What is the cosmological horizon? And why can't we see beyond it? So this is This is one that, oh, that was at the beginning of this lecture. Right, so cosmological horizon. So the universe has been around for 13.7 billion years. That means light, if anything existed at the time, the light from that, let's say a galaxy, has only had 13.7 billion years to travel, right? That's an enormous amount of time. So, you know, for the purposes of things that are within our galaxy and everything else, there's been plenty of time for light to travel. But if something is very far away from us, if something is so far away from us that the light from that something would take more than 13.7 billion years to get to us, then we wouldn't be able to see it yet, just because there hasn't been enough time in the universe for that light to travel to us. And I know a couple of you were asking me questions during lecture and I didn't have a chance to answer them. So if you still have the questions, I'm happy to answer them now. Otherwise, I'll just keep going. So anyways, we call that the cosmological horizon. It is the limit to how far we can see in the universe, given the fact that the universe has only existed for 13.7 billion years. So if there was something, excuse me, if there was something in the universe that was, let's say, 80 billion light years away from us, a galaxy that was 80 billion light years away from us, then light would start traveling, but it would still be pretty far away. It wouldn't have had time for that light to get to us. So again, we call that the cosmological horizon. It's what marks the part of the universe that we're able to see. Anything that is physically beyond that, we are not able to see it. And so this is one reason why we cannot answer the question of whether the universe is infinite or not, because there's a limit to how far we can see. Why can't we see anything beyond it? Because there hasn't been enough time for light to get to us, for light from those objects, if there's anything. To answer whether or not the universe will continue to expand forever, what are the two competing factors that we must consider? And I showed you a video about it where it showed galaxies with rubber bands around each other. That was supposed to be gravity, right? Gravity is an attractive force. Gravity wants to bring everything together. But then there is the expansion of the universe that we learn about through Hubble's law. So the universe is expanding, the space in between galaxies is expanding, but gravity is trying to bring everything together. So the two competing factors is the expansion of the universe versus the self-gravity of the universe. Why? Because the universe has mass and mass has gravity. So that's those are the two. In the case of the sun, it would have been gas pressure versus gravity, right? Self-gravity. So it's similar. In the case of white dwarf, for example, it would be electron degeneracy pressure versus gravity. So we see this over and over again in the universe. Right, so that's a pretty simple. What are the two factors again? Gravity versus expansion. So expansion of the universe and self-gravity, because the universe as a whole has mass and mass has gravity. The universe has mass, yes, and anything that has mass has gravity, right? Yeah. All right, so, all right, depending on the density of the universe, what are the 3 possible ways in which the universe may end? And I just realized that I have not written a question about this yet. So I need to make a note for myself to write a question about number 8. Okay, all right, so depending on the density of the universe, what are the 3 possible ways in which the universe may end? And let me go to that slide because it's probably easier to just show you. Yeah, here we go. So 3 possibilities depending on how dense the universe is. And when we look at the density of the universe, right? I mean, why are we looking at density to begin with? Because density is just mass divided by volume, right? Mass in a given volume. I just told you that you can't see the entire universe. You can only see a part of the universe. So what we do, and in fact, let me go back to that slide. Yep. So this is the visible universe. We don't know what's ahead or outside, but we assume that it looks just about the same by the cosmological principle. So we look at the universe that we can see. We measure the mass that we can see, and that mass is in the form of stars, gas, dust, black holes, as well as dark matter, which actually makes up the majority of the mass. So we measure all of that, and we divide it by the volume of the universe that we see, and that gives us a density. And that's the reason why we talk about density. So let me go back here. All right, so there's 3 possibilities. The 3 possibilities are that the universe is too dense, that gravity wins. Gravity, there's so much stuff, there is so much matter, there is so much gravity that gravity wins over expansion. And so even though the universe is expanding, at some point it'll reverse and it will collapse again. Just like I kept giving you the example of me throwing something, you know, up, and then at some point it reverses and then it comes back down. So in the same way, the universe is expanding, but if there's too much mass in the universe, then that gravity will win and it'll bring it back. The fate of that universe is to collapse again. And we talked about how they call this the big crunch. So the big crunch is one of the possible ways in which the universe may end if the density is too high. If the density, let me go to number 3, if it's not dense enough so that the universe continues to expand and expand and expand, then expansion wins. And we call that or they call it the big freeze, because everything will go separate. Oh, I don't have a good slide for that. But you know, the galaxies will go away from each other, and eventually everything will get cold, because you know the density of the universe will become lower and lower as everything expands, and you're not going to be able to form new stars. So there's not going to be enough heat, and everything will get very cold. So there's a question, should we know the terms big crunch, big rip, big freeze, closed universe, flat universe, open universe? The answer is I haven't written the question, so I can decide that right now. I don't want you to have to memorize these types of things, but you know, I think if I write the word big crunch, I think it's pretty obvious, right? That it means that things collapse. And I think if I write big crunch, I will clarify that it means it collapses. Big freeze, I think I will clarify that it just means that it keeps expanding forever. And then there's the one in between, which is if the density is just right, and if gravity balances expansion perfectly well, And so the universe continues to expand, but the expansion slows down until eventually it stops. The analogy with the pen, right, is a little bit weird, because it would be like if I throw the pen, up to the air, and it starts to slow down, but then it never falls back down again. It just kind of levitates and it stays there many, many, many years from now. The Big Rip, I will clarify the Big Rip in a little bit, because the Big Rip is not here, right? So there's the big crunch that happens when the universe is too dense, and there is the big freeze that happens if the universe is not dense enough. And then there's the one in between that just is, things slow down and eventually stop. Big Rip, I'll get to in a different question. So we're not there yet. All right. Big Rip goes with the next question. The next question is, what is dark energy? And what evidence do we have that it exists? So I gave you the three possibilities, right? No, I was right here. I give you the three possibilities of what might happen depending on how dense the universe is. But it happens, what happens is that neither one of this is what we observe. And I told you that for a couple of decades, people were trying really, really, really hard to measure the Hubble law in the past, right? And this, I did write a question about this, so pay attention. So let me go back to the Hubble law. Where's the Hubble law? Here's the Hubble law. The Hubble law, again, tells you how fast galaxies are going away from each other. And the slope of this is what we call the Hubble constant, H0. But if the slope is smaller, right, that means that the expansion of, that the universe is not expanding very fast, right? Because that means the velocities are not very large, even when you go to galaxies that are far away. So if, let me actually try to annotate. Yeah, there you go. Annotate, draw. Okay, so if the slope were not as large, right? Let's say that it looked like that, then it would mean that the universe is not expanding very fast. If the slope were greater, if it were, like that, it would mean that the universe is expanding very, very fast. And so what astronomers have been doing for a long time is trying to figure out if the slope has always been the same, or if in the past it was different. This is what we observe today, right? This slope here, so the one in between. That's what we observe today. But the question is it different in the past? And the nice thing about astronomy is that we can actually look at the past. We can see the universe, how it was a while ago or a long time ago, because the further we see in distance, the further in the past that we see, right? I mean, I always give the example, the sun is 8 light minutes away from us, meaning that we see the sun as it was 8 minutes ago. Proxima Centauri, the nearest star to the sun, is 4 light years away, which means we see that star as it was 4 years ago. So if we look at galaxies that are 7 billion light years away, we're going to be seeing them as they were 7 billion years ago. So that's what they did. Astronomers looked at very distant galaxies and they measured the Hubble law. And what they found was that the Hubble law is like this one, that the Hubble law in the past was actually less steep. It meant that the universe was going slower. It was expanding more slowly. And it has gone from there to what we see today, which means the universe is accelerating. So that's a pretty long answer. Do that. That's a pretty long answer. Oops. How do I clear? Okay, that's a pretty long answer for this, but that is the evidence that we have. Oh, okay, sorry, I haven't finished the thought. So what could possibly be causing the universe to be accelerating? The fact that it is expanding more rapidly today than it did in the past. And that's not, there's nothing in the physics that we know that we knew before this that would explain why things would accelerate. So again, right, in the case, like here's my mouse, if I throw my mouse up, it'll either slow down and come back down, or if I throw it with enough energy, right, it'll just keep going. But we've never seen a case where I throw something and then all of a sudden it accelerates. And in order to do that, in order to accelerate like that, it needs some extra energy. And we don't know what that energy is because it's a very strange behavior. So we call that dark energy. And so the evidence that we have is that the universe is expanding faster today than it did in the past. And that's the question that I included. And so what is dark energy? Dark energy is a mysterious form of energy that appears to be causing the universe to expand faster or at an accelerated rate. Can we say that the universe is expanding faster as time passes? Yes. Yes, that's right. So to answer the question about the Big Rip, even though I didn't ask anything about the Big Rip here, and therefore I'm not asking anything on the final, but just to tell you, the Big Rip is, clear all my drawings. I don't want to annotate. Okay, here we go. The Big Rip is what happens with a universe that not only is it expanding, but has this dark energy, an unknown form of energy that could be causing the expansion of the universe to accelerate. So it makes the universe not just accelerate, but accelerate. I mean, not just expand, sorry, but expand at an accelerated rate, faster and faster and faster, and until everything gets ripped apart, right? So because there will be a point where expansion will be faster or stronger, sorry, than not just gravity, but also electromagnetic force and the weak force and the strong force. So everything will fly apart, right? And everything will just get ripped. But again, I didn't ask anything about that in the final because it's not in your homework. So my bad. Homework 7. So would 7 also be gravity versus dark energy? Dark energy would enter within expansion. So even though dark energy is something that contributes to expansion, it's already included in expansion. So, all right. All right, so that's it for the expansion of the universe, and the last few questions refer to the very last lecture. So I think I've already been going for 40 minutes, so let me pick up the pace a little bit. It's my mouse. All right, so in summary, what does the Big Bang Theory describe? The Big Bang Theory describes how the universe went from a place that was infinitely small, infinitely hot and dense to the universe that we see today. So what the Big Bang Theory describes is how the universe evolved or how it changed as the temperature of the universe dropped and the density also dropped. And I had this figure from your textbook. So this is representing how the temperature is dropping as a function of time. And you can also imagine this is density. Density is dropping as a function of time. So what the Big Bang Theory does is it just describes how the universe changed over time as density and temperature decreased as a function of time in the universe, as the universe expanded. What happened during the Planck era? How do we know, or why don't we know? And that's why I had this. So I do recommend that you take a good look at this slide, or actually the slide that I had later in the class, or at the very end of the class, that is a little bit annotated. So take a good look at this, because that answers pretty much every question. So the Planck era is the very first tiny fraction of a second in the life of the universe. And what happened? We don't know. And the reason we don't know is because the conditions of the universe were so extreme that we don't have the physics to describe or to even try to figure out what was going on in the universe. The main problem is that quantum mechanics, and I have it right here, general relativity and quantum mechanics are two different sets of laws that we haven't been able to combine. So general relativity describes the very big, quantum mechanics describes the very small. And the problem with this particular, the very beginning of the universe is that the very big was very small. So you have to combine those two. And as some of the videos that I show you describe, we don't know how gravity acts over these tiny, tiny scales. So the Planck era, so the question is, so is the Planck era the time it took the universe to be created? No, it's not that. It's just that we don't know what was happening. After the Planck era, we know how to do the equations. We know what the rules of the universe were, the laws of the universe. But during that specific amount of time, which was tiny, we don't know what was going on. We don't know how the universe behaved. And that doesn't mean that people are not trying, right? People are trying really hard to do this, but we don't have answers yet. We don't know how it worked. And, you know, Stephen Hawking, I think a lot of you like him. He of course had all kinds of ideas about what happened during this time. But again, it hasn't been, it cannot be tested, and that's the problem, right? Any theory that, any scientific theory that people come up with needs to be tested. Otherwise, it's just a good idea. So right now we have a lot of good ideas, but not things that can be tested. So that is the significance of the Planck era. What are the four forces that we know today? Oh, is the Planck era going to be in the exam? Yeah, of course, there's a question on the homework. Anything that is on the homework is going to be on the test. What happened during the Planck era? Okay. What are the four forces that we know today? So gravity, electromagnetism. Actually, I'll just go to the slide because here we go. So gravity, the one that we talk about like all the time. There's electromagnetism, which is the most common one, right? When you turn on the lights, when you anything, I mean, everything that we do here on Earth is dominated by electromagnetism. And then there's the strong force, which I told you that it was that like Velcro force that if two protons touched, or if they were extremely close, then the strong force binds them together. But it's very weak as you go further away. And then there's the weak force, which is something that mediates nuclear reactions, such as fusion. These four forces, so this is today, in the present day, when the universe is pretty cool in temperature. The universe on average is about 3 degrees Kelvin, which is very cold. It's extremely cold. And today we have those four forces: the strong force, which is the strongest of all, then electromagnetic, weak, and gravity. Gravity is the weakest, but it can act over very, very large distances. So the whole idea is that these unify at higher temperatures. Electromagnetic force and weak force, they unify at temperatures that we can reach in the lab. So we know this for sure. Those two forces, instead of being electromagnetic and weak, become the electroweak. And then at even higher temperatures, we're pretty sure that they merge with the strong force. And then, things like string theory say that at even higher temperatures or higher energies, gravity also joins them all. And then there's this one super force. But we don't know about that one. We are pretty sure, we know for sure about the electroweak because we've seen it, we've measured it, and we are pretty sure about the strong force. So I think that's what the question asked. Which two unify at higher temperatures? Electromagnetic and weak. They go into the electroweak. Which three unify at even higher temperatures? Electromagnetic and weak, and strong force, those three. And those merge together to form what they call the gut force, the GUT force, which comes from grand unified theories. So the gut force. All right. So what is inflation and what caused it? Going back, can I repeat which three unify? Sure. So right here, you see it. Which three? Strong force, electromagnetic, and weak. Those three merge into what is called the GUT. And I spell it because I worry that with my accent, you might hear it wrong, but here it is. So GUT, GUT, which comes from grand unified theories. And it's right here. At even higher temperatures, grand unified theories predict the merger of electroweak and strong, which, those three forces, electromagnetic, weak, and strong, is called the gut force right here, the GUT force. Right. Okay. All right, so that leads us to inflation. So if those three forces, the gut force, were together in the past, then at some point, the strong force separated. Okay, I'll get back to your question in a second. So, so inflation, right? Sorry, I got distracted with the question. We were talking about how three forces unify at very high temperatures or very high energies. The electroweak with the strong, right? Electromagnetic, weak, and strong. So at some point, let me go back to, where is it here? So at some point, the strong force, as the temperature drops, right? We are going from hotter on the left to cooler on the right. So as the universe became cooler, the strong force separates from the other two. And when it separates, it releases an enormous amount of energy. It's similar to what happens with the atomic bomb. With the atomic bomb, the strong force is released because they split the nuclei of atoms. And so the strong force is released and it causes tremendous explosions. So the idea is that in the universe, when the strong force separated from the electromagnetic and the weak forces, it released energy into the entire universe. And this caused the entire universe to expand at a huge rate, right here. So inflation is the sudden and dramatic expansion of the universe when the strong force separated from the electroweak force. So it's called inflation because it's like it inflated the universe. It made the universe become a lot bigger. So, all right. I have a question in the chat. Can I repeat what happened during the Planck era? Can somebody say in the chat what happened during the Planck era? What happened during the Planck era? Come on, somebody write it on the chat. We don't know exactly. We have no idea. So the answer to the question, what happened during the Planck era, we don't know. No one knows. Very good. String theorists think that they know, but we don't know for sure. All right, thank you. Let's go back to the homework. We're almost done. So what is inflation? Is the rapid, the sudden expansion, dramatic expansion of the universe that happened at the end of the gut era. And it was caused when the strong force separated from the electroweak. Very good. And finally, recombination. So this is actually really important. And I feel, I was sad that I didn't have time to emphasize it in class because recombination is an incredibly important thing. And the reason it is so important is, there's so many reasons. So let me go to those slides and try to tell you a little more about recombination. Okay, this is a good slide to show. So here time goes from the bottom to the top. So this is the universe in the past, and then the universe, you know, way at the top would be in the present. So before and after, it also shows how the temperature is going down. The reason so what is recombination? Recombination is when atoms were first formed. Before recombination, there were protons, you know, there were nuclei of elements, hydrogen and helium, but there were no atoms per se. So if you remember, an atom has a nucleus and an electron that is going around. If you remove the electron, then you just have the nucleus, and you call that, you know, an ion. It's not an atom. So this is what happens in the central parts of our sun, in the interior of the sun. It is so hot that nuclei cannot have an attached electron, right? So you have a bunch of protons and a bunch of electrons, and they're all separate. They're not together. They're not, you know, the nice little, I guess I think I have, sorry. This is, you know, the nice picture of the hydrogen atom, where you have a proton in the center and you have an electron going around, and they're together, they're bound together, and they stay together forever. In the center of the sun, you don't have that because it's too hot. And what happens is the atoms get ionized, meaning the electrons get ripped, they're out, they're not attached to protons. And it's too hot because everything is moving very, very fast, right? Because of the high temperatures. So because of that, in the center of the sun, oh, keeps going back to that one. Because of that, in the center of the sun, or in the radiation zone of the sun, you know, in the core and in the radiation zone, you have a soup of electrons, free protons. And the problem with that is that photons, right, the particles of light, cannot travel unimpeded. Photons, as photons try to travel through this soup of electrons, they keep colliding with the electrons. They keep interacting with the electrons. And so they get bounced around. And I try to emphasize this a lot in class. The reason why you can see your screen is because the image, the light from the screen is traveling in a straight line to your eyes. And that's why you can see the screen. But if there were a bunch of electrons in between the screen and you wouldn't be able to see me. You wouldn't be able to see your screen because the light would get bounced around and you would just see like, you know, you wouldn't be able to see the image. It would just look bright, but you wouldn't be able to see the image. So light cannot travel through regions that are very dense and that have a lot of free electrons. I mean, it travels, but it gets bounced around and then you can't see through them. So if you were to take a voyage right into the center of the sun, you wouldn't be able to see anything. You would not be able to see light traveling. The universe, a long time ago, when keeps going to that, I don't know why. This is the one where I want. Okay, the universe, a long time ago, was so dense and so hot that that was what was going on there. There were electrons moving very fast and light couldn't travel in straight lines. So if you were to go back in time to, you know, close to the Big Bang, and you say, oh, I'm going to find out what happened in the universe at the time of the Big Bang. I'm going to take a travel machine. The problem is you would be in this soup of electrons and you wouldn't be able to see it. If you said, I'm going to observe how the universe formed, you wouldn't be able to, because the universe was what we call opaque. So like it says here, photons bounce around among free electrons. You would not be able to see it. And I just told you a few minutes ago, I was talking about how when we look to the past in the universe, we see the universe as it was a long time ago. And so you could think, well, let's just keep looking further and further away until we see the Big Bang. Here's the problem. You can't see, because at some point you're going to get to the point in the universe when the universe was opaque. And then you cannot see the Big Bang. So it's like you hit a wall. And I hope I'm not making you confused with this, but it is just so important that that there was a time when the universe was not transparent. There was a time when light couldn't travel freely in the universe. And that time is what we call recombination, right? So it's this moment when the universe was too hot for atoms to form. So as the universe became cooler and cooler, then finally protons and electrons could be together. Let me go back to that. So then protons and electrons could be together, and then light could travel in between them. And it wasn't bothered by these free electrons. And at that point, you can see. So when was that? When was the moment that the universe became transparent? That moment was 380,000 years after the Big Bang. Yes, I will ask that on the test. And the moment is called recombination because it's the moment when protons and electrons, or nuclei and electrons, could combine together. And at that point, light was able to travel. And that light that was able to travel, we can still see it today because it has been traveling all these years. And we call that the cosmic background radiation. So that's the next slide. So cosmic microwave background, sorry, or CMB, and it has been traveling, like I said, for more than 13 billion years. And again, why is it so important? Besides the fact that it marks the point where you can actually see in the universe, also because we do see this light. When we look further and further and further back in the universe, eventually we actually see this, and it's right here. This is what a map of the whole universe, right? So this is like a sphere of the whole sky taken around us, and then you unfold it, and it gives you this map. That's what it looks like. And that's sort of the leftover radiation that came from the Big Bang at the point that we were able to see it. So it's very important. It's so important that I have, like, let me see. Let me tell you for absolute sure how many questions. 1, 2, 3. I actually have 3 questions about this on the test. So if it's not super clear, please ask me. Let me answer a question. So the universe would be black, dark. No, it would be actually very bright. So if you were able to go back in time and, you know, look at, be in this part before it becomes transparent, you would just be light. You know, it would be super, super bright because you would be immersed in a medium that had very high density, and light would be, you know, bouncing around. And of course, there would be some light that would bounce right next to your eyes. But if you know, assuming that you didn't die, because of course you would melt and you would burn, but assuming you didn't, and you put your hand like this in front of you, you would not be able to see your hand. You know, even this close, like this close to your face, you would not be able to see it because light from your hand trying to go to your eyes would get bounced around, and all you would see is like this enormous brightness. All right. So please ask me if you have questions about this, because again, there's 3 questions about this on the. Yeah, go ahead. So somebody was going to ask a question and then they went away.
I can ask a question. For me, the question is the big picture of the universe. You know, at the end, the last part that you showed. I don't understand that part.
So great. I'm glad you asked, because this is like so second nature to me that I just assume that everybody knows already. What you're seeing here is the light that started traveling freely at the moment of recombination. And this is incredibly high contrast, right? Some parts are slightly brighter, some parts are slightly darker, but essentially what you see is light everywhere. And it is a little confusing because you see so much structure. But there were tiny variations. So some parts of the universe were just slightly hotter than others. So there were some temperature variations. I mean, you're seeing here light that has been traveling for more than 13 billion years in every direction of the universe. So you know, this is super high contrast, and the parts that look red and yellow are, let me see, 1/1,000,000th of a degree hotter than the dark parts. So you know, they like really cranked up the contrast, because there were very tiny variations in the universe. In some places it was a little bit hotter, in some places it was a tiny bit cooler, but 1/1,000,000th, right? 1/1,000,000th of a degree. So what happened is, at that point, light started traveling, and the places that were slightly slightly cooler, sorry, those were places where dark matter was able to accumulate more. And this is not on the test, but just for your knowledge. Those places like here, here, everywhere where you see blue, those are slightly cooler. And so dark matter was able to gravitate more toward those places, and all the atoms, sort of accumulated in those places. And eventually those became galaxies, and those became, stars, and that's why our universe has some structure, right? There are some galaxies in some places, and some voids or places with no galaxies in other places. But more or less pretty uniform. All right.
Thank you.
Of course. So for the final, will there be questions that were not on the homework assignments? Yes, thank you for asking that. So as I said, I'm on 93 questions right now, and I can't come up with any more. So what I'm going to do, and you guys have the benefit of knowing this, is I'm going to go back and I'm going to look at all the polls that I ever did, and I'm going to take a few of those questions and I'm going to put them on the test, because I'm out of ideas. So there was one question that I wrote down, question number 8 from homework number 10. I haven't written a question about that, so that'll be question number 94. And then there's 6 more that I need to come up with, and I'll probably just grab poll questions that were not on the homework assignments. And besides that, I may ask things that just things that I ask over and over again, right? For example, tidal forces. Tidal forces, and in fact, let's move on to the next part. So let me just see one more question. So we can't see the light from Hot Place Palace. I think there's a typo in the question. So if you don't mind asking again, because can I go over the Big Bang Theory again? Sure, there's not much to say about the Big Bang Theory, except that the Big Bang Theory describes how expansion and cooling of the universe. So the Big Bang Theory presumes that the universe started in a very tiny, hot, dense collection of matter and radiation. By radiation, we mean light. And the Big Bang Theory describes how it expanded and how it cooled down, and how that process led to the present universe that we observe today. How many questions about Big Bang? I'm not going to play this game. I'm not going to go and count every questions for every topic. So, I mean, you figure it out, right? I mean, it's a few questions in the homework. There's going to be a few questions. Would some of the questions be about outside examples? Right. So from outside examples, do you mean, what exactly do you mean? You mean like the videos that I played, or not unless I emphasize them in class, right? I mean, I will include things that I emphasize in class. So I was planning on meeting with you guys for 2 hours if necessary. So we can use this second hour to just go over some of what I consider the main topics, the main themes. Okay, so the question, can we see light from hotter places in the universe? Yeah, of course, we see light. Oh, I see what you mean. So yeah, it is a little bit confusing. And actually, if you don't mind, I'm not going to answer that question because I don't want to get people confused. So, okay. can I go back to recombination? Going back to the recombination, does the universe become transparent, meaning light passes through? Yes, exactly. How many vocabulary words did we go over? Do you mean like new terms? Because I don't know. I don't actually know. When will the recording of today's be posted? As soon as we're done. So I'll wait until I get the link, and yeah, and I'll post it tonight. Right. All right. So to answer your question about whether outside examples will be there or not, let me move on to give you just to remind you of, because maybe it's really obvious to me what are the things that I repeat over and over again, but maybe it's not as obvious to you. So let me switch to my iPad. All right. So let me. All right. So let's call this something like big themes. All right. Let's start with something that I spoke about from the very, very beginning of class. So I'm going to finish my thought and then I'll look at your questions because I have a couple of questions here. So one of the things that I've been talking about over and over again is the fact that light takes time to travel. Right? So, and I repeat it so many times, right? When we look at Proxima Centauri, we're seeing it as it was 4 years ago because it's 4 light years away. So it takes 4 years for that light to get here. So we are seeing things in the past. This is a concept that comes up when we talk about the cosmological horizon, right? It takes time for light to travel. So therefore, we can only see things that are, that have had enough time for their light to get to us. A subtopic of this, of course, would be a light year. What is a light year? And a light year. Okay, so not a light year, just the idea of light year. So what is a light year? What is a light year? How is it defined? Is it a unit of distance or time? And then, different things like what I told you, I think in some homework, like, I think I asked if there was a star that was ripped apart at the supermass in the center of our galaxy in the supermassive black hole, which is 28,000 light years away from us. But if it happened 5,000 years ago, would we know about it? And the answer is no, because there hasn't been enough time for the light from that event to get to us. So that's a concept that I brought up again and again. Another thing is, when we look at very distant galaxies, do we see them when they were younger or as they are right now, or when they were older? Like, are we looking into the past or are we looking into the future? Just stuff like that with that theme. So let me answer a couple of questions and then I'll get back to the themes. Okay, Ezekiel. So question about a black hole. So a black hole is not a vacuum cleaner, right? So let's jump to black holes are not, because I'm pretty sure I wrote something about that. Black holes are not vacuum cleaners. Meaning they do not suck things, right? They just have gravity like any other object in the universe. They have the gravity that corresponds to their mass. The thing with a black hole is if you do the representation in 2D, you know, where you have a black hole and you know, it curves space. And so if you're far away where universe is flat, then it's not going to suddenly like suck you in. But if you're close to the event horizon, where universe is very sharply curved and you're going in an orbit that gets you very close to the black hole, then sure enough, eventually you will fall in. And my drawings are terrible, which tells you why I always use slides. But if something does, you know, if even something that is far away, if it has an orbit, a trajectory that gets it close to the black hole so that it can circle around and eventually fall, that mass will be added to the black hole. And so let me do a different color. So the event horizon will grow a little because it got the extra mass. And the more you put into the black hole, the more the event horizon is going to grow. So this is actually what my thesis for my PhD thesis was about. You know, how do you get, like, since black holes are not just vacuum cleaners, like how do you, meaning the supermassive black hole in the center of our galaxy is not an AGN, right? It's not an active galactic nucleus because it's not eating things. And in order for it to become an AGN, an active galactic nucleus, stuff would have to fall into it. But the black hole itself is not going to suck the stuff, is not going to attract the stuff. So that means that somehow there must be some process that pushes gas and stars and stuff into black holes in galaxies that do become AGN. And you know, my PhD thesis was about that, and what I discovered was that it was mergers, galaxy mergers. When galaxies merge with each other, a lot of the gas gets pushed into the black holes, and then they form AGN. But I didn't cover that in class. So I think that hopefully that answers your question. Question? Okay. So a question about something that was asked on midterm 2. Why does an exoplanet with a higher surface temperature emit more infrared light? All right, I don't remember seeing a lot about this in the test. I mean, don't remember writing a lot about this, but it's not just an exoplanet. Any object that has a higher surface temperature emits more light, right? So even a person, if let's say you take a picture of me with an infrared camera right now, and then I start exercising so that my body temperature increases, you know, and I get a lot warmer. And then you take another picture, I'm going to look brighter in the infrared picture after I exercise than the infrared picture before I exercise. So the exact same body, if it's warmer, if it's hotter, it will emit more infrared light. Would some of the midterm questions be on the final? I don't know. I don't actually know. Possibly if it's one of this, if it's like something that I really want you to remember, then the answer is yes. Otherwise not very likely, but I don't make a lot of promises. All right, let's go on here, and please do keep asking questions. I said I would answer questions. So all right, so tides, tidal tails, no, not tidal tails, sorry, tidal forces. So tidal forces was something that we talked over and over again, right? And the idea is gravity, when you have gravity between two, it's an attractive force between two masses, right? You have mass 1 and mass 2. But gravity depends both on mass and on distance. And gravity goes down or as distance increases, right? So you feel stronger gravity when you're closer to an object than when you're farther away, which means in this example of mass 1 and mass 2, this side of the mass 1 feels greater gravity, so more gravity than this side, less gravity. Why? Because this side is closer to M2 than this side. And so what happens is all kinds of things, right? In the case of the Earth with the moon, the ocean of the Earth, gets pulled harder on one side, and the Earth gets pulled a little less, and then this side of the ocean gets pulled even less. So you end up with tides, right? With ocean tides. Also, when you have a galaxy with, nice spiral arms and another galaxy with nice spiral arms, and they come close to each other and, they're going to collide. Well, this side of the galaxy is going to feel more gravity than this side. And so what ends up happening is that the spiral arms end up getting deformed, right? So then you end up with galaxies that have this, what we call tidal tails. One more thing related to tides, right? Here's my black hole. And if a person decides to jump into the black hole, the feet are closer to the black hole. So they're going to be feeling more gravity. So the person is going to get stretched, and they're going to end up getting spaghettified. So what else? Jupiter, right? We had Jupiter with this nice spot, and there was a poor little comet that was coming toward Jupiter, and the comet felt the gravity from Jupiter, and it ended up getting broken into many pieces. So I would say this is something that we talked over and over again. So it's fair game, right? Because it was everywhere in the test. Oh, tidal tails. It just means when the spiral arms get unfurled or unwinded, or how do you say that? I'll say it in Spanish, desenredados. When they get pulled away from the galaxy, right? Let me go here. So you have a nice spiral galaxy with a bulge and arms, but then with the gravity from the other galaxy, it just gets elongated, it gets stretched. And so we call those tidal tails. Tidal because they came from tidal forces, but they're still made of little stars, right? It's just that they're like this big thing. Let's see. Not untangled. Yeah, a couple of you said untangled, but no, I just mean, no, I know because you said desenredado. Just pulled out, pulled away. All right. Okay, so, right. So hopefully that answered the question. Can I repeat what I said about Jupiter? Sure. So if you remember, Jupiter, the Jovian planet, so you should remember, you guys should remember what Jovian planets are. And you should remember how the solar system formed. Why not? It's important. When there was a comet, Shoemaker-Levy, which you don't have to remember the name, of course. When Shoemaker-Levy was coming close to Jupiter, this part of the comet felt more gravity than this part, right? The closer part feels more gravity, so it gets stretched. It gets stretched in this direction. And so it broke it. It broke it into pieces, and it ended up being something like 21 pieces or more that went to Jupiter. And so there were all these explosions that happened every time that one of the pieces hit Jupiter. So we talked about that when we talked about violence in the solar system. So, right. Very good. So going back to the question about the type of light that an object emits. So hotter objects emit more at shorter wavelengths, that's true. But a planet will never emit ultraviolet light because ultraviolet light is very high energy, right? So things like stars emit ultraviolet light, like our sun has some ultraviolet light, and that's why we have to wear sunblock and sunglasses. But things that are not as hot as stars do not emit ultraviolet light. They, things like light bulbs in our house, they will emit some visible light, but things that are cooler than light bulbs, like people or like planets, they emit infrared light. Right. All right, let me go on to see what else. All right, so another thing that we talked a lot about, and I'll just write it here, is conservation of angular momentum. If you remember, angular momentum was the product of mass times velocity times the radius of an object. And we talked about how in the absence of external factors, of external forces, if the radius of something shrank, then the velocity of that object had to go up. And so we talked about, and it doesn't just go away. If something is spinning, it will continue to spin until there's an external force that makes it stop. Right, so our planet is spinning, and as long as nothing hits us or there's some incredible gravitational perturbation, we will continue to spin. And so in the context of conservation of angular momentum, we talked about how the solar nebula, as it was shrinking, it started to spin faster, and that made it become flat like a tortilla. We talked about, I don't know, things falling into black holes, and as they spin around the black hole by conservation of angular momentum, they continue to spin, they form an accretion disk. We talked about neutron stars, right? When they shrink neutron stars are cores of stars, and as they shrink, they start to spin faster and faster. So that's another thing that we talked a lot about. What else? Yeah, I guess I have a couple of questions about, the formation of the solar system. Hopefully they're very obvious. I have a question about meteor showers, just because, it's the kind of thing that you might see within your lifetime. You should know where they come from. Same thing with the aurora borealis. So for me, things that I think you will encounter in life, like meteor showers. What are they, or how do they form? Aurora borealis. I mean, maybe you won't see one. I hope you see one. I've never seen one. I hope I will see them. Oh, things like the moon. Where did the moon come from? Why? Because, at some point you're going to have a niece or a nephew or a child or some little person around you, and they're going to ask you, what's the moon? Where did it come from? And I don't want you to say it's made of cheese. I want you to be able to answer those kinds of questions. Cool. Why we know the existence of meteors is important. Okay, meteor so I have a question about meteors. Meteor is the streak of light that you see when a chunk of something is falling through our atmosphere. So maybe that's not the question that you're asking, but I don't know. Meteor showers are the debris of comets. Yes, that's correct. Aurora is particles from the sun interacting with our atmosphere. Yes, that is correct. Very good. You guys are all prepared. So see, I'm asking like things that I hope you remember like forever, right? Not so much memorizing stuff. Oh, what are the most abundant elements in the universe, right? So most. I mean, now you can sort of put the whole picture together. You have hydrogen because it's the simplest element, right? It's just a proton, at least the nucleus, right? It's just a proton. And when it is actually an atom, then you have an electron that is going around it. It's the simplest of them. And protons form very early in the universe. And so you had hydrogen nuclei right from the beginning or very close to the beginning of the universe. And then I told you, like pretty early in the universe was so hot that there was fusion. So then you got helium, because hydrogen gets fused into helium. And so that's why those two are the most abundant in the universe. About heavier elements, right? For heavier elements require fusion in stars. And that's another thing that I want you to remember. Like when you talk about calcium or carbon or nitrogen or all of those things, they were not formed during the Big Bang. They were formed inside of stars. And so that's why you need generations of stars in order to build up this element. So heavier, again, I'm talking about carbon, nitrogen, oxygen, all these things that we take for granted so much, they were not around at the beginning of the universe. They had to be formed in stars. Should we be prepared to go in depth about the sun and stars? I'm not gonna, so for example, the process through which a star goes to go from being main sequence to being a red giant is very complex, right? It's very complicated. And even on the midterm, I didn't go through a lot of detail in that. So I probably will not ask about the details of that. I mean, no, I will not ask about the details, but I might still ask things like, why is a red giant red? Or will the sun become a red giant? I mean, I don't know if I asked that, but it's like more sort of bigger, more global questions about that. So let's see, what else? Oh, again, I did mention this at the beginning. Things like, well, no, let me, so gas pressure. We talked a lot about gas pressure. We talked about what happens to gas pressure when temperature is higher, what happens to gas pressure when temperature is lower. Gas pressure opposes gravity in stars, and they actually balance each other out, and that's why they remain the same. Gas pressure, you don't want a lot of gas pressure for star formation because you want gravity to win to make stars. And so you need low temperature so that gas pressure is not great. Things like that. I mean, this is something that we learned about it in one lecture, but then we kept bringing it back over and over again. So gas pressure is sort of an important thing, or very important. And also I said fusion, right? And not the details. I don't want you to give me like the details of how hydrogen goes into helium. We didn't even talk about it in class, but fusion happens in stars, and fusion requires very high temperatures because you need things to go very fast so that they can fuse together. Fusion leads to new elements. Fusion happened in the early universe, stuff like that. All right, let me. All right, so we talked about violence in the sun, and most of the violence in the sun, most of the violence in the sun, at least the violence that can get to us, was related to magnetic fields. And somebody's asking about magnetic field on Earth. So the sun is spinning, and the sun has a lot of ions, and we just talked about, because it has high temperatures, the electrons are free, they're not attached to nuclei, and so the sun is spinning, and that gives it a magnetic field. That's not on the test, but magnetic field lines of the sun go from the North Pole to the South Pole. And to begin with, they're nice and organized. But the sun doesn't rotate as a solid, right? It rotates faster in the center or in the equator than it does in the poles. And what that does is, over time, the magnetic fields of the sun become entangled. And so they start to get all, tangled. And so when you have some of those kinks going through the surface of the sun, they create sunspots. And then sometimes some gas goes up on those kinks, and those are prominences. So, and then sometimes when it gets super tangled, these things snap and they become flares. And when there's super big flares, then you call those coronal mass ejections or CMEs. I don't think I would ask anything too detailed about this, but you should know that the violence from the sun is associated with magnetic fields, because if the sun didn't have magnetic fields, none of this would happen. There would be no flares, no sunspots, no prominences, no CMEs. So, you know, it would be a different, much more boring type of star if there were no magnetic fields. And somebody was asking about the magnetic field on Earth. Earth has a similar thing. Earth has a liquid metallic molten core that generates a magnetic field around it. Well, let me. I don't know how to erase big things. Okay. So Earth, usually they show it with a tilt, right? The 23-degree tilt. And it has its magnetic fields too. Magnetic field lines. And so the relevance to this class was what we were talking about earlier. Sometimes the sun has this solar wind that goes in every direction. So of course, some of this solar wind goes to the Earth. And not just the solar wind, but also the CMEs, right? Sometimes a big CME comes toward Earth. And the Earth gets shielded from that CME with its magnetic fields. But some of the particles that come from the solar wind and the CMEs sometimes leak through, I should do a different color, green, because they're pretty. It leaks through the poles. And so that makes it down to our lower atmosphere. And as those particles interact with our atmosphere, they create this colorful displays of light that we call the aurora. So I don't know if you wanted me to go more into detail about that, but that's all you would need to know for the purposes of the test. Differential rotation is the term for the rotation of the sun. Yes, that's right. This is differential rotation. Could you be more specific about what part you want me to re-explain, or starting where? Let me go back to a different question here. Can I do a review on wormholes? I did ask something related to wormholes. But there's very little that you need to know. And I'll just tell you exactly what you need to know. Wormholes are theoretical things that we've never seen. We don't know if they actually exist or not, but they could possibly connect to different parts of the universe, or a universe to another universe. And they could connect a black hole with a white hole. There's speculation that if they actually exist, that if we could travel through them, we could appear in a different part of the universe in like almost no time. But they have a lot of problems, and that's the part that I want you to know about. What are, in fact, let me not go over them, you look them up. What are the problems? What difficulties would you have to overcome in order to travel through a wormhole? So that's sort of how I phrase the question, right? So it's actually a very easy question, the one that I put in. So hopefully it's all right. So can I re-explain the part about the sun? Let me just summarize it because we're sort of kind of running out of time, and I want to make sure that I tell you all the big themes. Differential rotation entangles the magnetic field lines of the sun. I'm not going to ask anything about that. What you need to know is that magnetic fields in the sun produce a range of phenomena, many of which are violent, including coronal mass ejections. Coronal mass ejections is when the magnetic fields get so tangled that they basically touch like a pole with another pole. And I didn't even cover that in class, so I'm giving you more detail. And the point is there is a huge ejection of matter into space. And coronal mass ejections can be bigger than the sun itself. They're enormous. Those sometimes come toward us, toward Earth. And when they do, thankfully, we have a magnetic field on Earth that shields us from the CME. But some of it leaks through our poles, and that's what I was showing. Oh, it's not drawing. That's what I was showing here. That some of the particles from the CME can leak through our magnetic fields, and those particles that come from the sun can interact with our atmosphere, and that produces what we see as the aurora borealis. All right. So let me move on to okay. Okay, this one. So another big theme is the electromagnetic spectrum. Maybe this is not super fair, but I do want you to remember the different parts of the electromagnetic spectrum, right? Starting from gamma rays, X-rays, ultraviolet, visible, sorry, not microwave, infrared, microwave, and radio. I do want you to remember that this is your short wavelength and long wavelength. Yeah, I guess this requires memorization, and I apologize about that. This is so important for astronomy, though. It is incredibly important, because we use all of these different wavelengths to study different things in the universe. And it is important that we know that, microwaves have longer wavelength than infrared light, and that like somebody was saying in the chat, ultraviolet has higher energy than infrared. So I did include at least one question, but probably more about this. Just understanding, the electromagnetic spectrum. So, I think it's pretty fair since I'm telling you that you need to memorize this. So I tend to ask questions in a way that you could guess it, even if you don't remember exactly which one goes first, but please do go ahead and memorize this. All right, what else? All right, so exoplanets. So we talked about the habitable zone. So exoplanets, I guess the most important thing is, how do you detect them? And what is the habitable zone? That's about it. All right, and then about stars, and I think that'll be it. So life of stars, right? I want you to understand the difference between, not the difference between, but I want you to understand the role that mass plays on stars, in the sense that mass will determine how long a star lives. Mass will determine whether it's bright or dim, whether it's hot or cool. So, it's multiple choice. So I don't ask very detailed stuff, but I do want you to understand, there's the OBAFGKM. You do not have to memorize that, by the way, but you need to know what it is and how to use that. And I say that you don't have to memorize it because I actually give it to you. But you need to understand that this is hot and this is cool. And therefore, this is short-lived, this is bright, this is big, this is blue, whereas M, this end means cooler, redder, long-lived, and so on. So I do want you to know the progression of star. Again, you don't need to remember the actual OBAFGKM. You don't need to remember that because I'll give it to you. But, and by the way, sometimes I define something in one of the questions, and then I ask something related in a different question. So make sure you look through the test because you might find the answer in a different question and so on. So please do. Should you remember the life sequences? Yes. Again, so I want you to know what happens to the sun, right? So you should know that the sun started as a protostar, then it became main sequence, and then eventually it'll become a red giant, a couple of times, and then eventually it'll end up as a planetary nebula. I do want you to remember that kind of stuff. And I don't know if I wrote a question or not, but you should know that high mass stars have a very similar life, just a lot faster, and they end up exploding, right? Our sun is not going to explode. That's something that is important that you know. But high mass stars do explode in supernovae, and eventually they become either neutron stars or black holes. What letter is after it's a G, and that's what our sun is, right? Do all planets in the habitable zone mean that there's life on them? No, not at all. So if you remember, habitable zone is just the region around the star where liquid water could exist. It doesn't even mean that there actually is liquid water, let alone life, right? It's just the region around the star that has the right temperatures, where it's not too hot, not too cold. All right, have about 5 minutes. I mean, I'm happy to stay longer, but I want to make sure that I finish everything I want to say within the 2 hours. I think that's about it. Yeah, I think that's about it. After that, we move on to black holes. But I think aren't black holes like in homework? Let me make sure. Homework 7, I told you. Right, so after what I mentioned, then we move on to homework 7. And then you can be sure there's going to be a question related to every single one of those questions. So should we make sure to know the anatomies of black holes and galaxies? Well, anatomy of a black hole includes event horizon and a singularity, right? But that's in the homework. So given this question, already that I will be asking something about the event horizon and I will be asking something about a singularity. So in that sense, you should. For galaxies, I believe there is a, briefly describe the main parts of our galaxy, meaning disk, bulge, halo. So you should know what a bulge is. You should know what the disk is. So yes. Can I explain why comets have tails? Sure. So anyways, let me just say, I've gone through everything. I mean, I have the test right next to me, except for the questions that I haven't answered, that I haven't written. But like I said, I'll probably go and look at the poll questions and probably pull them out from those because I'm out of ideas. So anyways, that's all that it covers, I think. So I will stay, for another half hour or so if you guys want, and I can answer questions, but otherwise we're pretty much done with the review. So yeah, I don't know if I should keep recording. Probably. I mean, people can stop watching it. So people who are watching this, you can go now. I'm just going to answer questions. So, all right. Thanks everyone, and I'll continue to answer questions.
Thank you, Professor.
Thank you.
No problem. All right, so can I explain why comets have tails and where do they stay most of their lives? Yes, of course. Let me do it here with the tablet. All right, so here's the sun. And then very far away from the sun, there is what we believe is a cloud that is spherical, but I'm just going to draw it as a circle, where there are comets. It's called the Oort cloud. Comets live very far, and this is not drawn to scale, of course. Comets are very, very far away from the sun, and they're frozen. It's a mix of snow, ice and rock, and they're frozen. They're just out there. Occasionally, they will have some, again, that word tidal interaction, meaning gravitational interaction. So maybe they bump into each other, or maybe they go very close to each other and the gravity of one pulls the other one. Or, maybe some other object, like a large object, passes around and then it changes the orbit of one of them. Whatever it is, it's usually a gravitational perturbation. It might send one of the comets into the inner solar system, and it's kind of like it falls and it goes around the sun and it changes its orbit. The orbit used to be, you know, around in this direction, but now the orbit is going to be this very elliptical, very elongated orbit around the sun. The frozen comet, as it gets closer to the sun, where it's warmer, right? Because it's cold here and it's warm here, or hot. But as it goes where it's warmer, all that ice starts to evaporate or sublimate, is the word, when it goes from solid to gas. And so it starts to develop this kind of like a cloud around it. And we call that the coma. But remember that the sun has this solar wind. It's like a wind of particles, a wind of ions that goes in every direction around the sun. So when that hits the comet, it starts to push that cloud, that form, because again, it was ice, it sort of melted and it formed this cloud around it, and then the sun pushes it. I mean, the solar wind. So it's solar wind. As the comet goes, you know, around the sun, here it's even closer. So of course the tail is going to be even longer. But remember that the speed of an object in orbit depends on the amount of gravity that it feels. So as the comet gets closer to the sun, it actually goes faster. So as it goes around the sun, the comet goes very fast. And so this is a short amount of time that it has a tail, because as it goes back to, you know, where it started, the tail is going to become smaller until it actually disappears. Why? Because the comet becomes frozen again, because it's colder. And then it'll come back here and it'll keep going around, right? But when it's far away from the sun, it's frozen. And so it doesn't have this tail. All right. Oh, so Daniel, you didn't notice any question of density waves. Yeah, that's in the homework. So let me, oh, in any of the homework. Really? I didn't? Well, okay, so it's these two, right? So where do stars tend to, oh, wait, sorry, I'm not, I'm not sharing the homework. Let me show the homework. All right, so where do stars tend to form in our galaxy and why? So they tend to form in the disk, because that's where you have the most gas, but they also tend to form in the spiral arms, right? Because, and that's where the density waves would come in. So that's the Y part. The spiral arms are density waves. And as material in our galaxy goes through those density waves, the density of the material, meaning, you know, gas, interstellar material, increases, and then stars form. So, and then why do the spiral arms of our galaxy appear brighter than the rest of the galaxy? Because, you know, it's basically the same question, because that's where stars form. And so there's a lot of high mass stars that are born there, and those are very bright. And then, you know, they die before they ever get out of the spiral arms. So that's why, you know, the brightest parts are the spiral arms. Also because it is a density wave, which means it has higher density in those regions. So higher density of everything, higher density of stars, higher density of gas. So that's, yeah, so that's all. I mean, that's the type of question that you'll get on the test. I mean, I'm not going to ask about why you get a phantom traffic jam, as the video talked about. It's just related to those two questions. All right. Let me see if I missed any other tails, black holes. Yeah. All right. Are there any other questions? Sure. All right, no problem. All right. Well, good luck to everyone. I hope it goes well. I hope it's not hard. I hope you come out with a big smile that I won't be able to see because you'll have your mask. All right. Good luck to you guys with all your other finals, and I'll see you on Wednesday then. All right. Bye.